So if you really stop and think about it, there is a profound, almost hilarious irony in the work you do every single day as a software engineer.
Oh, absolutely.
I mean, you sit down at your desk, you fire up your IDE, and you interact with these artificial intelligence models that possess what looks like absolute omniscience.
Right. They seem like they know everything.
Yeah, like you can ask a frontier model to write a complex Kubernetes deployment script from scratch, or, I don't know, translate a dense research paper from Mandarin, and it does it flawlessly in like 3 seconds.
The raw capability is
Yeah.
just staggering. Yeah.
But then you ask that exact same trillion parameter supercomputer a question like, if it takes 1 hour to dry 3 shirts on a clothesline in the sun, how long will it take to dry 33 shirts?
And the model, with just absolute supreme confidence, will tell you 11 hours.
11 hours. It's so funny.
It is, because it applies this perfectly logical linear math to a parallel physical process.
Mhm.
The model completely misses the physical reality that the sun shines on all the shirts at the exact same time.
Right.
I mean, a 6-year-old child intuitively understands that, but a massively parallel supercomputer trained on the entirety of the public internet just fails completely.
We see it all the time. Like, when that AI overview famously suggested adding non-toxic glue to a pizza recipe to keep the cheese from sliding off.
Oh, right, the Reddit comment.
Exactly. It read a sarcastic Reddit comment,
Yeah.
saw the statistical correlation between cheese slipping and glue, and just recommended it as a culinary solution. It has the sum total of human knowledge, but zero physical intuition.
Zero.
So, okay, let's unpack this. Because that gap between superhuman coding ability and, frankly, sub-toddler physical intuition is our mission for tonight's deep dive. We are looking at a stack of research notes focused on what might be the single biggest bottleneck in artificial intelligence today, which is common sense reasoning.
It's a huge topic.
It really is. We talk a lot on the show about parameter counts, context windows, synthetic data. But tonight, we are talking about the quest to get a machine to understand the absolute basic underlying reality of the physical world.
Yeah, and to even approach the scope of this bottleneck, we really have to isolate what researchers actually mean when they use the term common sense.
Right, because it's not just street smarts.
Exactly. In our daily lives, we use it to describe good judgment, right? But in AI research, the definition is far more foundational. It refers to the massive, almost invisible body of background knowledge that every human being takes completely for granted.
Like what kind of knowledge?
So it covers the laws of physics, temporal awareness, and just fundamental social intuition.
It's the stuff that is so incredibly obvious to us that we never even bother to say it out loud.
And that omission is the core of the problem. Researchers actually refer to this as the below-the-waterline paradox.
The iceberg analogy.
Exactly.
Yeah.
Picture all of human knowledge as an iceberg. The explicit knowledge, the historical dates, the API documentation, the recipes, the Python tutorials, that is the visible tip of the iceberg jutting out above the ocean.
Right, the stuff we actually bother to document.
Right. That is the text we deliberately write down, publish, and, feed into training data sets. But the massive foundational bulk of human understanding sits entirely below the waterline, totally invisible to the web scrapers.
Because no one writes a blog post to announce that dropping a bowling ball on your foot hurts. Or like that when you walk into a room, you can't just phase through a solid brick wall.
It would be absurd to write those things down. Humans communicate with a shared baseline of physical reality. Like when an author writes he dropped his keys, they don't append a footnote explaining that the keys fell downward due to gravity, hit the floor, and made a metallic sound.
Right, the reader already simulates that entire physical sequence in their head. The text is just a highly compressed shorthand for reality.
Exactly. Highly compressed.
Let me put this into an engineering context for everyone listening. It's like trying to train an AI model to be a master architect by only feeding it 2D blueprints.
Okay, I like that.
The blueprints are incredibly detailed, right? But they never explicitly contain the rule that gravity pulls downward, because every human architect already knows that. If that underlying rule isn't actually encoded in the lines of the blueprint, the model doesn't see it.
It just learns where to draw lines.
Right. It doesn't know why the lines hold up the roof.
That analogy really hits the fundamental limitation of the current training paradigm. I mean, large language models are text engines. Their entire universe, their whole conceptual space, is constrained by the written word.
Just tokens.
Just tokens. So if this critical foundational common sense appears minimally or not at all in their training data, the model is attempting to build a robust reasoning system on top of a void. It's expected to navigate a 3D physical world using only a 1D string of text tokens that deliberately omit the most important rules of the game.
But hold on, I need to push back on this void idea for a second.
Sure.
Because I'm looking at these benchmark scores in our notes, and the reality is that the frontier models feel like they have common sense. If I prompt a top-tier model with, "I left a block of ice out in the midday sun, what happened?" it tells me it melted into a puddle.
It does.
It doesn't tell me it turned into a butterfly. And the research specifically calls out these massive test suites like HeliSwag, PIQA, Common Sense QA. These models are scoring in the 90th percentiles.
They are crushing the benchmarks.
So from a software engineering perspective, if the test suite is green, the code works. Are researchers just moving the goalposts because they refuse to admit a language model actually figured out physical reality?
I get that. It is incredibly tempting to look at a 95% score on HeliSwag and just declare victory. But we have to look at how those tests actually function and what the model is doing under the hood to ace them.
Okay, break that down for me.
Let's take HeliSwag as an example. The benchmark feeds the model a scenario, something like a woman is outside playing with a frisbee. She throws it to her dog, but the dog misses, and the frisbee. The model then has to choose the most logical continuation. Does the frisbee land in the grass, or does it achieve low Earth orbit?
And the model correctly picks lands in the grass almost every time.
It does, but we have to separate test performance from underlying capability. The model isn't running a physics simulation in its latent space. It's performing a brilliant, highly complex form of statistical pattern matching.
It's mapping words.
Right, it maps the co-occurrence of words. In its massive training data, the tokens for frisbee, throw, miss, and grass cluster together in a high-dimensional vector space. The tokens for frisbee and orbit do not. It's simply predicting the most statistically probable sequence of text.
It's a statistical illusion.
Yes, a very convincing one.
He's like, okay, think about a junior developer who just copies and pastes a highly complex block of code from Stack Overflow into the code base. The code runs perfectly. The feature works.
We've all been there.
Right. And to an outside observer, that junior dev looks like a genius who deeply understands the system architecture. But if you ask them why the code works, or ask them to modify a fundamental variable, they completely break the application because they only copied the syntax.
Exactly. They don't actually understand the state of the machine.
The language model is the junior developer in that scenario, pasting together the syntax of reality.
That's a great way to put it. It doesn't know what temperature actually feels like. It has no internal physical representation of a solid transitioning into a liquid. It's mapping the words of physics, not the laws of physics.
Right.
This statistical proxy creates a breathtakingly convincing illusion of comprehension. But because it relies on correlation rather than ground truth understanding, it's fundamentally fragile.
Which means the illusion inevitably shatters the second you step outside the well-lit, highly documented paths of the internet. And that brings us to the edge cases.
The gaps in the reasoning.
Exactly. The notes highlight that the failures in AI reasoning aren't just random hallucinations. They cluster in very specific, predictable areas, novel situations, precise physical reasoning, and causal understanding. So for the engineers listening who are trying to stress test their own AI agents, what is the practical difference between correlational understanding and causal understanding?
The difference is whether the system knows that something happens versus knowing why it happens.
Okay.
Correlational understanding just notices that event A and event B show up together in the training data. Causal understanding means grasping the physical mechanism connecting them. Let's look at a classic physical reasoning scenario.
Sure.
If you prompt a model with, "I am holding a glass over a tile floor and I open my hand," the model will reliably predict that the glass falls and shatters.
Because the phrases dropping a glass and shattering on the floor are highly correlated. Like
Yeah.
every murder mystery, every clumsy anecdote on Reddit mentions the glass breaking.
Right, but let's introduce a novel situation, something that disrupts the statistical frequency. You tell the model, "I'm holding a lightweight plastic cup over a thick, heavily padded shag carpet and I open my hand."
Oh, that's tricky. Because dropping a cup is still highly correlated with spilling or breaking, but the physical materials have completely changed.
Exactly. If the model is over-relying on text correlation, you might confidently tell you the plastic cup shatters on the carpet. Or, even if it avoids that trap, it still might fail to calculate the nuanced physical outcome that the plastic cup will likely bounce slightly, tip over, and make a soft, muffled thud.
It can't simulate that.
No, it cannot calculate the outcome from first principles. It doesn't understand the density of plastic, the shock absorption of shag carpet, or the physics of impact.
Because none of that math is in the text. It only knows the words. And the notes mention this exact same gap appears in quantitative estimation.
Yes, the estimation problems are fascinating.
Like the classic interview question, how many ping pong balls fit in a Boeing 747? An LLM will give you a spectacular answer to that, breaking down the volume of the fuselage and the diameter of the ball. But it's only doing that because that specific Google interview question has been written about 10,000 times online.
So try changing the parameters to something entirely novel. Ask the model to estimate how many 3D printed, star-shaped plastic ornaments can fit into the trunk of a 2018 Honda Civic alongside a folded wheelchair.
Oh man, the model loses its mind.
Completely loses its mind. It applies completely linear math to irregular 3D shapes. It cannot visually and spatially rotate the objects in a simulated space to make a common sense estimate. It just multiplies the volumes and spits out a mathematically precise, physically impossible number.
So if scraping more text data from the internet isn't going to solve these physical and causal gaps because the underlying reality just isn't captured in text, how on earth do we fix this? Are we just stuck?
That question is driving one of the deepest, most intensely debated philosophical and engineering shifts in AI research right now. It's called the embodiment hypothesis.
I have to admit, when I first read this section of the notes, it shifted my entire perspective on where this technology is going.
It's a massive paradigm shift.
The hypothesis essentially argues that you cannot learn physical reality through a screen. Are researchers really saying that until an AI model literally inhabits a physical robot body, walks around a physical room, and stubs its metaphorical toe on a coffee table, it is never going to truly grasp common sense?
That is exactly what they're saying. The argument is that true common sense fundamentally requires interactive physical experience.
Yeah.
Think about how a human toddler learns about the world.
Right.
They don't sit in the crib reading Wikipedia articles about gravity and material science. They grab a wooden block and throw it. They observe the arc, they hear the loud noise it makes on the hardwood floor. Then they throw a stuffed animal and notice it behaves completely differently.
They drop the plastic cup on the carpet and they drop the glass on the tile. They are running continuous, real-time physics simulations.
Yes. They interact, they observe the consequences of their physical actions, and they build a causal model of reality from the ground up through continuous sensor-motor feedback.
That makes so much sense.
The embodiment hypothesis challenges the entire current trajectory of AI. It asks, can an intelligence confined entirely to a server rack, processing nothing but tokens of text, ever achieve the physical, social, and temporal understanding that biological creatures gain simply by moving through the physical world?
It reminds me of that classic philosophical thought experiment, Mary's Room. You know the one.
The color red, right?
Exactly. You have a brilliant scientist who lives her entire life in a black and white room. She learns every physical, mathematical, and neurological fact there is to know about how the color red works. She knows the exact wavelength of the light. She knows how the retina processes it. But until she walks out of that room and actually sees a red apple, she doesn't truly know what red is. The text is not the territory.
That is a perfect analogy. And the implications for the industry are massive. If the embodiment hypothesis holds true, then simply scaling up our current language models, throwing another trillion parameters and another trillion pages of synthetic text at the problem will yield severely diminishing returns on reasoning.
We hit a wall.
We hit a wall. We won't be building a smarter entity. We'll just be building a more elaborate, articulate statistical illusion. To cross the threshold into true causal understanding, the models need to touch the world.
And researchers are actually trying to do this right now, right? It's not just theory. They are building vision language action models.
Yes, VLA models.
They are taking these massive brains and plugging them into robotic arms, trying to map a text token, like pick up the apple, directly to the motor torque and camera feed of a robotic gripper.
They're attempting to ground the floating text tokens in physical reality. When the robotic gripper attempts to crush a plastic cup versus a glass cup, the neural network registers the difference in physical resistance. The token for glass suddenly gains a multi-dimensional weight that goes far beyond its proximity to other words in a sentence.
It becomes real.
Right. It becomes grounded in physical consequence.
I want to pause here and bring this directly back to the listener, because at this point in the deep dive, it is incredibly easy to think, wow, fascinating philosophical debate. But whether the AI understands gravity or just simulates gravity really doesn't matter to me as long as it outputs the right JSON payload for my app.
But that is a massive trap.
Exactly. Understanding the physical world isn't just an abstract philosophical milestone for an AI. It is the absolute, non-negotiable prerequisite for taking action.
This points us toward the absolute cutting edge of software engineering today, which is planning and autonomous agents.
Right. If you are an engineer right now, the holy grail is no longer just building a chatbot that can answer trivia or draft an email. You are trying to build agents, systems that can actually do things autonomously.
Real-world tasks.
You want an AI agent that can negotiate a meeting schedule, organize a complex file system, book a flight, or even independently debug and deploy code to a production environment.
And every single one of those autonomous tasks requires planning. Planning is the cognitive ability to look ahead, evaluate multiple different potential paths, and choose a sequence of actions to achieve a specific goal. But planning relies almost entirely on an underlying foundation of common sense.
Because how can you plan a sequence of actions if you don't actually know what the physical, temporal, or social effects of your actions will be?
An agent must know what actions are physically and logically possible in a given state, and it must accurately predict the consequences. If you ask an AI agent to manage your calendar, and it lacks common sense about physical space and time, it might schedule a physical in-person meeting for you in New York at 1:00 p.m. and your next physical meeting in London at 2:00 p.m.
It knows the text string for New York, it knows the text string for London, and it knows the word meeting. But it completely lacks the below-the-waterline context that human travel across an ocean takes 8 hours, not 0.
Right, and the difficulty of planning compounds exponentially. You aren't just evaluating the immediate next step. You have to think 5, 10, 50 steps into the future.
It cascades.
Exactly.
Yeah.
If your common sense predictions about the environment are even slightly off on step 1 by step 5 of your plan, your agent has completely deviated from reality. It gets stuck in endless loops. This is why you see current AI agents endlessly clicking the wrong part of a screen, trying to interact with a hidden pop-up window.
Oh, I've seen that so many times.
The statistical illusion might hold up for a single turn of conversational text, but it shatters when attempting to execute a multi-step plan in a dynamic, unpredictable environment.
So if we want agents that can actually function autonomously in our world, they have to understand the fundamental rules of our world, not just the text describing the rules, but the causal physical reality beneath them.
We are trying to teach machines the very things we are completely oblivious to knowing ourselves. I mean, we have successfully taught AI the most complex, highly specialized knowledge humanity has ever produced. We've given them our medical textbooks, our legal codes, our architectural blueprints.
But the absolute foundation, the pull of gravity, the weight of a stone, the unbroken forward march of time remains stubbornly below the waterline.
It really does.
It is the ultimate blind spot, and it continues to be the most frustrating, fascinating hurdle for the smartest models and the most brilliant engineers on Earth.
And honestly, until the embodiment gap is closed, engineers will always be managing the friction between the illusion of comprehension and true, grounded understanding.
Which leaves us with a truly wild concept to think about as we wrap up tonight. We spent a lot of time talking about the embodiment hypothesis, the idea that AI needs a physical body, sensors, and motors to truly learn common sense by interacting with the world, much like a human toddler does.
Right.
But think about the mechanical reality of that. If we actually succeed, if we train an AI by letting it control a synthetic body for millions of hours, will it actually learn human common sense? Or will it develop a strange, uniquely machine common sense?
That is the million-dollar question.
Because the way a titanium arm equipped with digital torque sensors and LiDAR experiences gravity, texture, and impact is fundamentally different from how a human hand packed with biological nerve endings experiences those exact same forces. The causal reality the machine learns might end up being perfectly precise, perfectly accurate to the laws of physics, but still entirely alien to us. Keep questioning the obvious. We'll see you on the next deep dive.